And for today's presentation, we have Matt Taylor and Nicholas Moss from Bunt & Associates joining us. Matt is a transportation engineer with a background in travel demand forecasting, traffic operations analysis, and transportation design. He's led several R&D initiatives at Bunt to extend their knowledge and expertise in new areas. And Nicholas is a civil EIT with experience working in various public and private sector capacities in both the US and Canada. At Bunt, he is a transportation analyst who has completed traffic impact assessments, travel demand forecasting, parking and circulation studies, and transportation demand management programs. Today, they will be speaking about transportation network efficiency with demand response services. So we're lucky to have these great speakers lined up, and please give them a warm welcome. I'll pass it off to you guys now.
Thanks, Cameron. So the subject of this presentation is on transportation network efficiency with demand responsive services. My name is Matt Taylor, and presenting with me today is my colleague Nicholas Moss. So first we'll give a brief overview of the scope and purpose of this research. So what are demand responsive services? They are shared transportation systems that provide dynamic on-demand service rather than service based on fixed routes or timetables. In this presentation, we will refer to these services as DRT, for demand responsive transport. Familiar examples of DRTs today are taxis and transportation network companies like Uber. And in the future, networks of shared autonomous cars and shuttles could provide demand responsive transportation throughout cities without requiring the cost of a driver. When we think about the long-term future of transportation, it's possible that both private vehicles and transit systems could largely be replaced by DRTs. And there are many studies that have looked at this question and evaluated the overall impacts on a city when compared to private vehicle use. They've considered scenarios with and without existing transit systems in place. The primary difference with this study is that we looked at a more direct comparison between DRT services and traditional fixed route transit services. Specifically, how would the performance of very high frequency fixed route transit compare to a DRT system? And this is an important comparison because in a future where AV technology allows for low-cost DRT systems, this technology would also allow for low-cost, high-frequency transit services. So by understanding the advantages and disadvantages of DRT systems when compared to both private vehicles and fixed-route transit, it allows you to plan for future transportation networks in ways that provide the greatest overall benefits to users. For this study, we used a software tool developed by PTV that simulates DRT services called MaaS, which stands for Mobility as a Service. This tool allows you to set parameters like vehicle capacity, pick-up drop-off points, maximum waiting time, and maximum detour factors, and then simulates DRTs with an optimized service algorithm. And this picture shows these simulated DRTs in the network with the number of passengers in each vehicle. So that's an overview of the study. Now I'll pass it off to my colleague Nicholas Moss, who helped set up the model and carry out the analysis. He'll walk you through our approach before getting into the results and conclusions.
Thank you, Matt. So for this study, we developed what we call a generic city model. And the purpose of using a generic model rather than studying any particular city is that it's flexible. It allows us to gain a high-level understanding of how well we expect the transportation modes that we're modeling to perform in any city. So let's go through what the model looks like. The base city model is this simple 10 by 10 arterial street grid network, with a traffic zone that's centered on each arterial intersection or node. The population of our city is 250,000 people. For comparison, here is our model overlaid at scale on Richmond, which has a population of 220,000 people. The distance between the arterial nodes in our model is 800 meters, which is fairly representative of a typical North American city. And the distance from the traffic zones where the trips originate to these nodes is 400 meters. So in other words, the average person has to travel 400 meters to get to their nearest arterial intersection. The travel times for private vehicles are 1.5 minutes in between arterial intersections, and also 0.5 minutes from the traffic zones to the intersections. These are equal despite the different distances because the driving time along arterials is significantly faster than along local roads. The walking time to the arterial intersection is 5 minutes, and we haven't specified a walking time between arterial intersections just because pickup and drop off is always going to take place at the closest arterial intersection or at the traffic zone itself. We've divided our city up into different zones and assigned a land use type based on each of these zones. Our analysis assumes that the downtown urban core is off-center, kind of to the north of the city, as can be seen in the picture. And the number of trip productions and trip attractions per hectare for each of the land use types has been set based on representative traffic zones in Vancouver's regional travel model. These are some examples of traffic zones in Richmond that compare, and they have similar demand to the from the regional travel model. So we can see that the most dense urban core, quote unquote, zone includes places like Richmond Centre Mall and City Hall. Here's another way to illustrate those trip productions and attractions in each traffic zone. We can see that the trip attractions are much more concentrated in the city core, whereas trip productions are somewhat more spread out throughout the city. Next, the number of trips between each traffic zone was estimated using the gravity model, which is a fairly typical procedure used in this sort of trip distribution analysis. In our simple cities case, the gravity model assigns the number of trips between two zones simply based on the distance between those two zones, which reflects that people generally do not tend to make their trips any longer than necessary. Also, the total number of trips was based on the statistic that an average person makes 3.3 trips per day. Total set of trips is also distributed time-wise throughout the day, with the time of day profile being based on regional survey data. Study period for our analysis is 6 to 9, which is consistent with TransLink's frequent transit network hours. So that was the generic city model. Next, let's look at the transportation modes that we assessed within the model. First mode is private vehicles, which should be familiar to everyone. In this model, all trips were assumed to be completed by one person only. So no groups of people are traveling together, and private vehicles all transport one person only. They provide direct door-to-door service, no waiting time, and they travel at 32 kilometers an hour on our arterial street network. And that's an average speed that includes like stopping at traffic lights. Next mode is single-occupant demand responsive services, which we call DRTS. An example of DRTS would be a traditional taxi, or it could be Waymo's autonomous taxis. DRTS provides door-to-door service like private vehicles, but it has a 5-minute pre-booking time, meaning that when you're booking a trip, the earliest possible option to start that trip is 5 minutes in the future. And then that's followed by a 10-minute maximum wait time, accounting for variability in when the vehicle is actually going to show up. However, the pre-booking time is not actually counted within our overall journey time because we've assumed that you would make the decision to go on a trip slightly in advance of when you're actually ready to start that trip. We also assess multi-occupant DRTs, which we call DRTM. And an example of this type of service today would be Uber Pool, where unrelated riders heading in the same direction can choose to share a ride. For this study, the DRTM vehicles have a maximum capacity of 15 people, and they do have the same 5-minute pre-booking and 10-minute maximum wait time as DRTS, but the service is provided to and from arterial intersections rather than door-to-door. So this means the passengers have to walk 5 minutes from their home or from their traffic zone to the nearest arterial intersection in order to be serviced. At that point, however, The trips on the DRTM don't require any transfers, so you'll be dropped off at the arterial intersection that's closest to your destination. The routes that the DRTM vehicles take are determined dynamically with an optimized algorithm. That's part of the PTV software that Matt introduced earlier. And also we've set it so that no passenger's travel time is going to be more than twice or 2 times longer than if they drove directly. The speed of these guys is the same as private vehicles and as DRTS, but we've also added 20 seconds per stop for pickup and drop off. And the last mode is a standard transit bus with an 80-person maximum capacity. Service is provided on a grid of linear routes on every single arterial road in our model, and they have 5-minute headways on all of the transit lines throughout the city as well, which is a very high level of transit service, but it's potentially more realistic in an autonomous future without drivers. The travel speed of the buses is 24 kilometers an hour, inclusive of stops. And note that because the buses are only stopping at arterial intersections, that means they're having stops around every 800 meters, which is more similar to an express bus. So at this point, I'll turn it back over to Matt to discuss the model's results.
Thanks, Nicholas. So now that we've outlined the model, let's get into the results. First, we will review journey times. Next, we'll assess vehicle kilometers traveled. And finally, we'll look at the number of vehicles required. But before we get into the results, I want to make it clear what we modeled and analyzed. The number of trips for each mode was specified as 15% of all trips, so it's not an estimate of mode choice. And we look at the performance of each mode serving the exact same set of trips. The performance results are reported for each mode, not for the city as a whole, and also travel time changes resulting from congestion are not modeled. And the reason that we structured the study this way is that it allows for direct comparisons of performance between the transportation modes. For instance, we can ask questions like, how many vehicles would be required if all trips on transit buses instead used DRTM? So the first performance metric we looked at was journey times, which are split into walk times, wait times, and ride times. As you would expect, each of the alternate modes requires additional journey time as compared to private vehicles, which had an average journey time of 10.1 minutes. DRTS was found to take 84% more time, with this increase due to the time required to wait for a vehicle to arrive. Also keep in mind that the 5-minute pre-booking time is not included in the total journey time for DRTS and DRTM. DRTM was found to take 129% more time. This increase is due to the 10-minute walk time to and from the arterial stops. The wait time for this mode is less than with DRTS, and the reason is because most of the time you would have been waiting is instead spent walking to the pickup location. And finally, buses required 136% more journey time. With the chosen service parameters, the overall journey times for DRTM and bus are very similar at 23.1 and 23.8 minutes. So to summarize the results in the previous slides, the finding here was that journey times increased as compared to private vehicle use with all of the shared transportation modes. So given this, many people using private vehicles today may still choose to use them in a future where DRT services are increasingly available. The next performance metric we looked at is vehicle kilometers traveled, or VKT. And note that this VKT result is for the same 15% of total trips that are modeled for each of the transportation modes. So you can think of a change as the VKT that would be added or removed from the network if that 15% of private vehicles switched to an alternate transportation mode. With DRTS, there was an 8% increase in VKT compared to the same set of trips in private vehicles. This increase in driving results from vehicles traveling without passengers to their next pickup location. DRTM resulted in 3 times less VKT than private vehicles. And the 5-minute frequency bus service throughout the city would serve the same set of trips with 10 times less VKT than with private vehicles. So the results here show that a shift to DRTS could result in additional congestion due to the increased vehicular travel. A shift to DRTM would result in significant VKT reductions, although the benefits of a shift to buses would be even greater. The last performance metric we looked at is the number of vehicles required. And keep in mind again that this is based on the 15% mode share. So you can think of it as a decrease in the number of private vehicles, or the number of private vehicles that would be removed from the network if 15% of people switch to one of these alternate modes. With DRTS, 6 times less vehicles were required. With DRTM, around 30 times less vehicles were required. And finally, the 5-minute frequency bus network would require about 140 vehicles, which is almost 300 times less than if the trips were taken with private vehicles. And we did check here that peak link flows in the network and confirm that there was adequate bus capacity with this configuration. So to summarize, major decreases in the number of vehicles required were found with each of the shared modes, from 6 times less with DRTS to 30 times less with DRTM to almost 300 times less with bus. So once again, the benefits of buses far outweighed DRTS and DRTM. And here's a summary of the overall results. So the key finding here is that although there are benefits to DRTM compared to private vehicles, the benefits of a high-frequency bus network were even greater. Another way to look at these results is that replacing the bus network with a DRTM network would require 3.5 times more VKT and 9 times more vehicles to serve the same set of trips, while only providing minor improvements to journey times. This illustrates that even though there are benefits to DRTM, the efficiencies of a fixed route bus network can far exceed that of an optimized network of DRTs. So one of the key findings of the previous analysis was that fixed route buses can provide users with similar journey times using far fewer vehicles and VKTs than DRTs would. This raises the question of whether the best strategy for utilizing autonomous technology is to provide even higher frequency fixed route services. And here we look at a somewhat extreme example where the transit network is replaced entirely by the same set of 15 passenger vehicles used with DRTM, which we'll call microbuses. The microbus network provides the same grid of linear arterial routes, and the lowest frequency is 5 minutes, but to meet the peak travel demands on each route during each hour of the day, this frequency is increased up to at most 1 microbus per minute. Compared to DRTM service, this resulted in a 5% reduction in average journey time, from 23.2 to 22 minutes. There's also 2 additional things to consider here when comparing the journey time results. The first is that DRTM also requires a 5-minute pre-booking time, which is not included in the journey time, while microbus does not. This allows for more spontaneous trips and frictionless planning with the microbus network. The second is that in this simplified model, everybody walks 5 minutes to the pickup location. But in reality, some people will have shorter walk times. And this would directly reduce journey times using the microbus network. But with DRTMs, reductions in walking time may be offset by additional wait time. Looking at VKT, the microbus network required 2.5 times less than DRTM. And compared to DRTM, 4 times less vehicles were required with the Microbus network. So to summarize, using the exact same type of vehicle, the high-frequency Microbus network provided improved journey times with 4 times less vehicles and 2.5 times less VKT. This indicates that this type of ultra-high frequency service could be provided at a lower cost given the need for fewer vehicles and less kilometers driven. Many users might also prefer the Microbus service, regardless of cost. It provides shorter travel times, particularly for those already close to a stop, and requires less pre-planning. Although transfers between bus lines would be required for many trips, given these extremely high frequency of service on these routes, these transfers might be considered a minor inconvenience by users. The design of these services could also aim to make transfers as smooth and simple as possible. So next, we wanted to look at some, how different characteristics of the city could impact the performance of each of these modes. And one of the parameters we tested was the share of demand using each mode. These are the demand shares that we tested. The base demand scenario used a 15% demand share, while a low and high demand scenario were also tested with 5% and 25% demand respectively. Again, each mode is modeled in isolation with the exact same set of trips. So these demand shares would apply to all modes. As noted previously, congestion effects are also not considered in the model. So the performance impacts of changing these demand shares is directly attributable to the transportation modes themselves, rather than to interactions between modes or changing travel times due to congestion. So here we found that private vehicle journey times were around 10 minutes for each scenario, with some minor differences due to the inherent variability of the model. Going from a 5% to a 25% mode share, DRTS journey times went from 1.8 times longer to 1.9 times longer than in private vehicles. DRTM journey times remained essentially level at around 2.3 times higher than private vehicles. And bus journey times also remain level at around 2.4 times higher than private vehicles. So the finding here was that mode share had a negligible impact on journey times, although it's worth noting again that congestion was not considered in this model. And the next metric we look at is VKT. And here we saw that shifting from a 5% mode share to 25% had a more material impact. But first I want to highlight something about this chart. All the results are set relative to the performance for the same set of trips using private vehicles. So if you look at the left side, you can see that although the private vehicle numbers vary between scenarios, these are all set to 100%. For instance, at a 5% mode share, this is VKT, there's 169,000 vehicle kilometers traveled from private vehicles, but at a 25% mode share, there is 870,000, and both of these are set to 100%. And the reason is that this allows for a more meaningful comparison between results. For instance, at a 5% mode share, this resulted in 169,000 VKT, while at a 25% mode share, it was 931,000. But obviously, you would expect VKT to increase as more people use this mode. So is this result better or worse? Well, you can tell by comparing it to private vehicles, and you can see that 16% additional VKT was found with a 5% mode share, while only 7% additional was found at 25%. So relatively speaking, DRTS performance improved as more people use the service. Comparing DRTM to private vehicles, 2.4 times less VKT was required at a 5% mode share, while 3 times less was required at a 25% mode share. And for buses, 3 times less VKT was required at 5% and 17 times less at 25%. One thing to note here is that between each of these scenarios, no additional buses were required to meet the peak demand, resulting in the same 52,000 vehicle kilometers traveled for each scenario. Although the bus VKT doesn't change, the amount of private vehicle VKT removed from the network does, so the performance of the bus network increases as the demand share increases. To summarize the VKT performance results compared to private vehicle use, the key item to highlight here is how the relative metric improves or declines as the share of people using this mode increases from 5% to 25%. So as an example, the numbers in red show how much more VKT was required with the RTS than with private vehicles. And as we saw, this declined from 16% more to 7% more, which is an 8% improvement. So when we talk about improvements here, that's what's being compared. So for DRTM, the relative VKT improved 19% between 5 and 25% mode share. And for bus, the relative VKT improved 81%. So while the increased mode share improves relative VKT for each of the shared modes, by far the biggest benefits are for buses. And here's another way to look at those results, which directly compares the shared modes. The horizontal axis is the travel demand share using each mode, and the vertical axis is the VKT by that mode. The results show that VKT for the demand responsive modes increased linearly, while the bus VKT remained level. And it should be noted that at an even higher demand share than those assessed, additional buses may be required during the peak hours, but it'd probably be a relatively minor increase. So the next thing we looked at is vehicles required, and at a 5% mode share, 12,500 private vehicles were required, while at a 25% mode share, 62,500 private vehicles were required. Comparing DRTS to private vehicles, 5 times fewer vehicles were required at 5%, while 7 times fewer were required at a 25% mode share. With DRTM, 19 times less were required at a 5% mode share and 34 times less at a 25% mode share. And for buses, 92 times less were required at a 5% mode share and 460 times less at a 25% mode share. For the relative number of vehicles required, DRTS improved 28% between 5 and 25% mode shares, DRTM improved 44%, and bus improved 80%. So again, the largest improvements resulted from increased mode share went to buses, but DRTM and DRTS also saw improvements. Looking directly at the shared modes, with increasing travel demand using these modes, the number of vehicles required by the DRTS services increased while the number of buses remained level. And this is an overall summary of the previous results. So relative to private vehicle use, improvements were found for all of the shared modes. However, the largest improvements were for bus services. And another way to look at this is that replacing bus trips with DRTM, the relative VKT is 320% worse, and the relative number of vehicles required is 180% worse when shifting from a 5% to a 25% mode share. So what this means is that as demand for shared modes increases, it makes sense to focus more resources on high-frequency fixed-route services. Additionally, when demand for shared modes is low, DRTM might outperform bus or at least provide more comparable performance. For instance, at the lowest 5% mode share tested, only 30% more VKT was found with DRTM compared to buses, although 5 times more vehicles were still required. So the last parameter that we tested here was the impact of city size. And the base city model we used was a 10 by 10 arterial grid with a population of 250,000. The small city model we tested was a 5 by 5 grid, and the large city model was a 15 by 15 grid. And the population density, proportion of zones of each type, and the layout of the city remain the same between each scenario. As relevant comparison cities, you could think of Mission, Richmond, and Surrey. And these models all assume the same 15% demand share for each mode used in the base model. So average private vehicle journey times were 7 minutes for the small city, 10 minutes for the medium city, and 12 minutes for the large city. Comparing DRTS to private vehicles, 2.2 times longer journey times were required in the small city and 1.7 times longer in the large city. So the relative improvement found, improvements were found as the city size increased because the driving time was a larger proportion of the total journey time. And this makes the relative impact of the waiting time required with the DRTS and DRTM modes less pronounced. Comparing DRTM to private vehicles, 2.5 times longer journeys were required in the small city, while 2.2 times longer journeys were required in the large city. And with buses, 2.8 times longer journeys were required in the small city and 2.2 times longer in the large city. Summarizing the results, again here, but just to note, the numbers to the right are the performance of individual scenarios from the charts we just looked at. And the percent improvement is calculated from the change relative to private vehicle use between the small city and large city scenarios. So the relative journey time improved 23% for DRTS, 11% for DRTM, and 22% for bus between the small and large city scenarios. For VKTs, 85,000, 531,000, and 1,468,000 were found in the small, medium, and large cities, respectively, with private vehicles. Comparing DRTS to private vehicles, 11% more VKT was required in the small city and 8% more in the large city. For DRTM, 2.6 times less was required in the small city and 3.1 times less in the large city. And for buses, 7 times less was required in the small city and 12 times less in the large city. So as city size increased, the relative VKT improved 2% for DRTS, 17% for DRTM, and 41% for buses. And here we compare the shared modes directly. And the finding is that as the network size increases, the VKT for the demand responsive services increases exponentially at a greater rate than the bus services. Next, we look at the number of vehicles required. This was about 9,000 in the small city, 38,000 in the large, medium city, and 84,000 in the large city for private vehicles. Again, this is related to the 15% demand share, which could be considered the proportion considering to switch to an alternate mode rather than every private vehicle in the city. So comparing DRTS to private vehicles, 8.2 times fewer were required in the small city, while 5.6 times fewer were required in the large city. For DRTM, 43 times less were required in the small city, well, 21 times less were required in the large city. And for buses, 310 times less were required in the small city, and 270 times less were required in the large city. To summarize, with each of the shared modes, as city size increased, the number of shared vehicles required increased relative to private vehicles. And this translates to 47% worse for DRTS, 111% for DRTM, and 17% for buses. And comparing these directly, we see that same exponential increase in the number of demand responsive vehicles required and smaller increases in the number of buses required. So in the large city network, we're looking at 4,100 vehicles for DRTM versus 317 vehicles for buses. Overall, the results show that with increasing city size, buses have the largest VKT performance improvements and the smallest decline in the relative number of vehicles required. And again, we can look at this to see how replacing the bus network with DRTM network would impact performance under these different scenarios. So when shifting from a small city to a large city and comparing DRTM to buses, the relative journey time of DRTM is 14% worse. Relative VKT is 41% worse, and the relative number of vehicles required is 81% worse, or 80% worse with DRTM. And this indicates that the benefits of transit become even greater in larger cities and service areas. So those were the results of the analysis. What are the overall conclusions? First, a switch from private vehicles to DRTS would result in additional VKT, but it does require far fewer vehicles. Next, a switch from private vehicles to DRTM would reduce VKT and require even fewer vehicles than with DRTS. And last, despite the benefits of DRTM, a high-frequency fixed-route bus service could provide similar travel times for users, but with far fewer vehicles and VKT required. An important note here is that for any of these transportation modes, they could be autonomous or manually operated. Although we don't directly look at costs in this presentation, the cost of operating any of the shared modes could be substantially lower because a driver is not required. But the thing to keep in mind is that the relevant comparisons are between either autonomous or manually operated services. Because when AV technology becomes available for one mode, it will likely be available for all of these. And the key policy implication that we found with this research is that in a future where autonomous vehicles are readily available, utilizing this technology to provide a network of high-frequency fixed-route buses can provide even greater benefits than on-demand door-to-door services. And as transportation professionals, we should be planning for these types of services. So that's it for the presentation, but before we open it up to discussion, I'd like to thank some of the people who helped with it. Arjen van Andel, formerly with PTV, facilitated the partnership between Bunt and PTV on this work. And Dr. Alex Bagazzi from UBC and Stefan Wekic from PTV provided us support and guidance developing the model we used for this research. So thanks everyone, and I'll open it up for questions or discussion.
Thanks for the presentation, Matt and Nicholas, and everyone else, feel free to turn on your cameras and ask questions as you want. But maybe I'll start off with one. Were you guys surprised by how much worse, I guess, DRTM performed compared to buses? Because I guess that was a bit of a surprising finding for me, especially around journey times and things like that.
Yeah, I think it was somewhat of a surprising result, kind of based on initial research, I had started to look into this a while ago and did a little bit of mental math, and it made me think, you know what, I think the probability of someone being able to share a route with another person is going to in some ways be proportionate to the number of different routes there are through the network. And that kind of gave me the thought that, well, in a network, in a gridded network of buses, you actually have far fewer routes than you do when you're looking at these dynamic services that are, trying to kind of find both the, a shared horizontal and vertical route. So that was kind of the initial mental math that led to this, which did give me the expectation that these were the results that would be found. And I think it is what makes it interesting, because it is such a significant difference. I think it was kind of expected at the outset, but when I first kind of came to the thought that, hey, these dynamic demand responsive services might not perform as well as some might expect, I think it was kind of a surprising insight.
And on an even wider level, I feel like we've heard of quite a few stories at this point where a bunch of tech folks get together in a room and try to figure out ways to solve transportation issues. And every single time they just end up reinventing the bus. So we kind of already expect that buses are the best of the bunch in terms of the transportation networks that can be provided. And it was pretty neat to see just how much so that was the case with this analysis.
Yeah.
I will mention too, though, sorry, just one more thing. We really were focusing on fairly large cities in this analysis, and even the smallest city we assessed for a BC standard, that's still quite a large city. So it would be interesting to look at these, quite a bit smaller cities, 5 to 10,000 population. And in that case, I wouldn't be surprised if we saw kind of really good performance metrics on the DRT services. I guess the only trap you might fall into with that is if they become really popular, you're starting to increase the demand share, and then at some point you might cross over to where these fixed route services are actually higher performing again.
Yeah.
But maybe at that point people would be kind of locked into their preferences with these door-to-door services.
Yeah. Since Erica had her camera turned on first, I'll let her go next. Oh, sorry, you're on mute right now, Erica.
I guess I'm just wondering, if you had an ideal city and you were going to use a combination, what would you recommend?
I think probably where it would be interesting to kind of look at tying them together is using the demand responsive services to maybe look at the first mile, last mile type problems in smaller, harder to reach pockets of cities where it just is quite difficult to provide typical fixed route transit. And in this case, we've got this really clean gridded city in all cases, but that's not true of every city, and there might be pockets that are hard to serve with transit. So yeah, I think it would be really interesting to do a follow-up that looks at tying together in an optimal way these on-demand dynamic services and fixed route transit. But I think the principle would still hold that really the desire is to use them to get people to these fixed route transit services, because once you start kind of running demand responsive services on a whole larger network, you're starting to lose those efficiencies.
And for an actual example, if we look in Metro Vancouver, we can kind of see a potential case study happening in Maple Ridge, where they have kind of their one transit corridor where there's a rapid bus that's already coming like every 10 minutes at this point. And then there are buses, fixed route buses at this point, that run every 2 hours. So how is that going to work for anybody, that you're on one bus that comes every 10 minutes and somehow have to transfer to a bus that comes every 2 hours? So if we can replace that very sparse local bus network with some sort of DRT network that gets people to the high frequency rapid bus, then that could be a place where this could be valuable.
Okay, Paul, I'll leave it up to you next.
I missed the early part of the presentation, so I wasn't sure the modeling aspects of it. I think the results, the outcomes are fairly intuitive. I think if you have a high frequency fixed route bus network, that surely is the way to go. It's interesting on the city size. There was a comment you made about the penalty on the transfer on a grid network. That wasn't something that you model, right? It was just an assumption.
Maybe I can take that one. Yeah, so we do model it in the sense that there is a wait time that is included in the model, both for catching the first bus and catching the second bus. So if you are making a transfer, then that is included. And it's also not included if your trip happens to be only along one bus route. So therefore you only have to catch one bus.
Okay. I see that Bassett is here, and he's a great believer in the penalties on the transfers. So
I don't have a camera today, but I do have a question if I may.
Yeah, go for it.
Let's hear it.
Yeah, great presentation and interesting findings here. So you mentioned early on that the network, the vehicle performance is not measured. Does that mean like there was no sort of like delay impact on the network? Is that right? And I'm just wondering if that's the case, are we leaving some benefits on the table? Because as you get more and more people into, buses and so forth, you have less vehicles on the network, which should mean less congestion. So just wondering about those network-wide effects.
Yeah, that would certainly be the case, and it wasn't modeled here. And I think the reason for that is if we're trying to kind of account for everything at once and account for the impacts and changes in congestion resulting from shifts to new transportation modes, it's hard to know, it's hard to be able to compare things directly anymore. So it's hard to know, was there a benefit from a shift to DRTM because of the various congestion effects that happen in the network, or was it simply that type of service kind of fundamentally performs differently regardless of the congestion in the model? So by not modeling, congestion impacts and interactions, it just allowed us to provide these really direct comparisons of these different types of services. But I think it would be kind of an interesting follow-up to look at more of a real city model and look at these interactions. But yeah, certainly any sort of shift to DRTM or DRTS resulted in far fewer kilometers driven. So presumably that's going to have a result in overall congestion improvements in the model.
Yeah, agreed. But yeah, no, I agree that we wanted to keep the analysis simple and control a certain number of variables. Yeah. Thanks.
Margaret Gibbs asked one question in the chat as well. She asked if there's any examples of DRTM already deployed in BC.
I do know that TransLink did a fairly quick pilot project on Bowen Island, of all places, where they, it's a very low population and low density and definitely not a grid network. I don't actually know what the results of that were. I'm not even sure if TransLink has published them. They were fairly recent, just before the pandemic, if I remember correctly. And I don't know of any others. I'm not sure if anyone else does.
Amy, it looks like you might have a question.
Yeah, I kind of have a question. Do you think DRTM might be a good solution for, I guess, I don't know how to call it, but like specialized services? I'm just thinking about HandyDAT, for example. HandyDAT, it's like a service for people with mobility needs. So I think it's been running with a very primitive technology where you just call TransLink and you say, I need to be at the hospital by X time, and I'm in a wheelchair. And then someone does a manual route planning to pick up everyone. So I've never used it myself, but I have family members who have, and it's very inefficient because these buses kind of do a big loop around to make sure they catch everyone in a certain time slot. Do you think DRTM might be have potential at least in like solving some of those inefficiencies?
Well, I guess if you think about it, it is kind of DRTM already, in the sense that that is the kind of type of services that would be providing. It is, you know, having several passengers with different pickup drop-off points and trying to kind of service it in a way that's efficient. And I think that definitely on the technology side, I think there's probably some improvements that could happen there, but it is, yeah, I guess it is kind of an example of a DRTM service and maybe the difficulties of actually finding kind of optimal and efficient routes in with those types of services. But on the flip side,
go ahead, Matt.
Sorry, I was just going to say, you know, we talk a lot in the presentation about how, you know, fixed route buses are a really great answer to a lot of problems. That doesn't mean they need to be the only type of service, and certainly, you know, making people with disabilities transfer more than once is not a good thing to do. So I think still having that type of DRTM service for HandyDART does make the most sense.
Yeah, what I was going to add was that the way that we've set up the model as well, pretty much we have asked the model to tell us what the optimal number of vehicles is. So for each of the analyses that we presented, the number of shared vehicles, both DRTS and DRTM, is the quote unquote correct number that is best for the city. And it's very possible that for a real world scenario like HandyDART right now, they don't have enough vehicles, or they don't have enough drivers, or everything is too spread out that it doesn't really make as much sense, because yes, we're in a very large city, but maybe the actual demand mode share gets so spread out that having everybody along one route means that if you're going out of your way to pick up somebody else, that means you're going 30 minutes out of your way. And so we try to control for those things within our model by saying that, okay, your travel time in a DRTM is not going to be more than twice as long as if you drove yourself. And those just might not be possible in a real world scenario when you don't have the money or the resources.
Yeah, I mean, I think, sorry, I just wanted to add one more thing, as my mom works for a cancer agency, and I think there's a lot of single occupant trips to and from BC Cancer to pick up medication for people who are at home, right? So if there was a way to help people who need to make these specialized trips to get there in an efficient way, I think that could reduce a lot of the single occupant trips to the hospital area, for example. But maybe you guys can sell your idea to TransLink and help them revamp their program a little. But thanks for insights.
Thanks, Amy.
And do we have any other questions right now? I guess if not, we can wrap it up here, Matt, unless Matt and Nick have any kind of final words.
Nope, that's great. Thanks.
Okay,
Nothing
well,
for me. I'm happy to get a 3-minute lunch before my 1 o'clock meeting.
Well, thank you very much for presenting, both of you. It was great to have you guys here today. I know I really appreciate it, and I'm sure everyone else did as well. And I'll give one last call out for the AGM that'll be coming up in early December. So hopefully we can see lots of you guys there at that. And with that said, have a great day, everyone.